My name is Bernhard Krüpl-Sypien. I say it again for just to recap it, or shortly Bernhard. And please tell me if I step too far away from the microphone, because maybe I don't realize it's as good as you do. So, what is this all about? What I'm going to talk about? So what we did is we created a semantic model that unifies access to content, visual, and functional aspects of a web page. So the idea was to come up with some other method for encoding web pages to have an easier way to work with them for what we do. And this model, we thought about this model, and we imagined this model for tasks in information extraction and accessibility, as I'm going to show you shortly. And the model in its core has visual objects. So and this what makes it different from the current or the most predominant methods you do it now on the DOM tree on the web. So this talk is first I'm shortly going to show you what the current issues are with current DOM-based approaches and which are the challenges we can possibly face in here. Then I'm going to shortly introduce our versatile model. I'm going to talk about how we put data into the model. Then I will talk about how these Gestalt theory concepts inspired us for some aspects of the model. And I'm going to show you how we work with data in the model and how we're going to use it. So, okay, first, issues. Why are we not happy with DOM approaches? As we all know, and I'm okay, that might be too easy for you. But of course, in DOM HTML models, we're talking about trees. And still, most information extraction on the web is being done on the DOM tree. But it's important to know and keep in mind that HTML itself is not self-contained. You need external sources in addition to that to make a rendering. Might be CSS standards, but there are also some conceptual ways that are built into browsers how they render stuff. So basically, it's the way the standards are defined. So, and what's also interesting, while CSS is being meant to separate content from presentation, many websites just don't work if you just look at the content in HTML code, because the layout is essential for understanding them. So if we look at some snippet of an HTML tree, obviously we have it's a tree, yeah? And what information extraction does right now is it works on X paths like this. So if you want to drill down to some particular element in some on some web page, you have to construct paths like this. And the problem with these paths is they are pretty page specific and they are not robust at all. And what we thought is, why are we still working on this level? I mean, when we what is the correct way to consider visual hints when you look at pages? So, because in some way you could say that HTML and CSS are actually just transport protocols. So what designers do when they envision a web page, they usually fire up Photoshop to create a web page. And after that, they hire someone who does their page and encodes them in HTML and does CSS and so on. And why do we then struggle to try to interpret HTML and CSS when the visual content is meant to be understood? So this was our main reasoning behind trying to do something different in the information extraction stuff. And then we are also working on accessibility. So if you look at any web page, as you all know, it's with saccadic eye movements and whatever, it's extremely fast to pass for us what it's about, what it is all about, and where's the content, where's the navigation, and so on. Yeah? But what you also know is that for blind users, it's a lot more problematic because everything is being serialized into a one-dimensional representation. Might it be on a braille line like this, or in a voice representation? And what they do now, because visually impaired and blind users are smart, is they find quick ways how to travel through web pages in alternate ways. And many times they have to step back onto the HTML level because only there they can find hints how to navigate. Of course, there are web accessibility standards, many of them, but they are slowly adopted, and we guess they will never be adopted for all web pages because many times publishers just don't have time to include them or just don't care or whatever. So it would be fine to have something that also makes it easier to work in this domain, and something that's good to make it accessible to those users. So okay, here it is. This is our motivation. We wanted to come up with a better model than the DOM for information and extraction and accessibility. And this should be some kind of versatile model in which we can throw in all kind of information and somehow get it out back again by querying and information extraction. So this should be something that we could play around with. This is not to solve some particular task in information extraction and accessibility, but more like a playground and a model where we can dump everything into it and get it out later. And what helped us in understanding it, and again, I mean, we had DocEng now, and this might be also trivial for you, but it was not for me. It was thinking about the phone, right? What happens if I'm somewhere in a remote place and I don't have internet access, but I do have my phone and I need some important information from a web page, and I call home, I call my mother, and ask her, so please can you look up that web page and tell me where's this venue I need to go to? Then she will probably explain me somehow what she sees on the page, and I will say, yeah, please, okay, can you see this white, there's some white box somewhere there, could you go to this? I think this information that I need is down there. So this is what inspired us as well, that there's some kind of visual language that you use on the phone. And what we would like to strive for, and don't say that we accomplished it, but of course, yeah. But what we'd like to strive for is to come closer to this kind of language that they speak on the phone. So how can we formalize it? So what we came up with is a model that's grouped into 9 layers. And there's an increasing amount of information from bottom to top that's being added to the model when we work with it. And the basic element, and this slide is going to come back again once again, the basic element in this model is a visual object. So what we consider visual objects from a web page are words and images. And the first part is crucial. So it's words. We're not going for text nodes because text nodes often are not of sufficient granularity because there can be line breaks. And the way a browser layouts those text nodes can differ. So we're looking for words. And basically, we're extracting the basic properties of this, so position, sizes, content, all the usual stuff. And also, we extract images, but we don't analyze images in detail, so we just extract plain images as black boxes. So, now, how do we store it? Coming from this, from the web area, it was natural for us to choose a semantic storage format, so basically RDF. So what we did is we store every visual object we find on a page in a form of a triple. So we have, I don't know if you're familiar, basically most of you are familiar with that. Who's familiar with yeah, okay. So we have subjects, predicates, and objects, and our subjects are the visual objects. So how we do it? For example, a visual object, here it's named I678, that comes from somewhere for now, is being annotated with additional information that we find about it. So for example, we know it has this content string, but there's more and more information about the object that's getting into it. So getting back into this model, we start on a lower level by employing a component that I'm going to show you right now on level 1. So what you see here is on level 1 we have the source code, which we also still have available. on level 2 of the model, we have hints of DOM and CSS and from JavaScript. And of course, we're not so stupid that we throw this information away because it's very useful in the later processing. But we somehow want to have it together with all the geometric and other information that we can get. So that's why we have on the upper layers, on level 3, we have a raw geometric layer where the information about visual objects and attributes is stored. And after that, this information is increasingly enriched by some small processes that are being deployed onto this model. And I'm going to show what kind of information this is going to be. So, but how do we get the information into the model in the first place? So we created a Mozilla-based component, which does the rendition with the Gecko engine, and then stores its findings into the model. We have something that we call Enrichers. So these are little programs in different languages. So we can have them in Java, in Ruby, in other languages that just augment additional facts into the model. So they try to they retrieve some visual objects from the model, find some relationships between them, and write additional information back into the model. And since this is being a triple store, we can do some automatic reasoning that can help us. So the first step is this Mozilla component. Of course, we decided to rely on something that's available already because we didn't want to replicate our own web browser. And it does an awful complex CSS and JavaScript stuff. And JavaScript is important because an increasing number of web pages is only rendered correctly, or how it's meant to be consumed, when you also apply JavaScript to them. So because there's Ajax and all this more modern stuff that's actually loads some parts of the web page dynamically. We implemented this as a TCP/IP server, so basically as a web service where you can connect to, you supply an URL, and you will get out back a list of visual objects with all the basic properties. The visual objects are tokenized from the text nodes into word ranges by using the getBoundingClientDirects method, which is now exposed by CSS object model view. And this is the way how we get the data. It's quite fast. I mean, the talk before talked about performance. I have to say that in our problem that we have now, performance is not that big an issue because we are dealing with single pages and we are dealing with accessibility users who actually want to read one particular page. So we have no scalability issues here. So a sample output can look like this. So when we deploy our browser component onto a particular URL, this is what you get back in notation 3 formats. I'm showing here notation 3 because of brevity, because it's clearer. So a visual element would be an HTML element here, which has a particular document index so that we can back onto the original HTML source if we want to do so. And we derive some information from the web page. So this is here the geometry code, which is the position and width and height. X means that it's being tokenized, so it's a sub-element on sub-element level. And there are some HTML dependencies, so we can, of course, have somehow replicate the HTML tree in here by including the HTML child-of and sibling stuff. And we can get some color and font and some rendered information about this visual element, so how it really looked like. But this is only the first step. And this is far away from what I've told you before about what we talk about on the phone. So how can we get closer to all of this information? So we were, as I said before, we were inspired by the Gestalt theory, which was a movement which was established in the late 19th and early 20th century by these two Austrian-born people who basically talked about Gestalt, which is a German word that does not translate exactly to one particular English word, but it's something between shape, form, pattern, figure, something like that. So it's something that that helped us in understanding, and most of you, at least the faces I'm looking into it, are completely aware of. So, you know these laws. I mean, there's something you can establish relationships and grouping based on proximity, on similarity, on closure, on continuity. And what can we do about that? For example, you have the distinction between figure and ground. So this is actually, if you do it on a superficial level, it's quite easy. And we wanted to be pragmatic everywhere where we could. On a superficial level, you just have to consider the set index of a document and consider all the elements which are basically on the first level as foregrounds and the other elements on the background. And so you just write this back into the visual objects. This does not, of course, this does not include any nesting or partly covered stuff. This is just a very naive way of looking into that. For proximity, we can look at adjacency. We can look at neighbors and distance. And what we will do is we will just write for each visual object in our model, we'll just write these adjacency information, neighborhood information. So an element, particular element is north of another element, or it is south of another element. It has a particular margin, like this margin south of 29 pixels to another element, which is written on the bottom. For similarity, when we don't look at the content, which we don't do, we have to look at color, size, and font properties, so basically all the stuff that our browser gives us. And for that, we can look onto color code and geometry code, font code, just write this back into the model. Continuity closure is something interesting, because I think it's when you think about a table that's, for example, that's been interrupted by some banner ad or something like that. It's quite easy to immediately realize this just by looking at the alignment. So if you can, what we do is we deploy a process in our model, and we establish a left-aligned, right-aligned, top-aligned, etc. relations between all visual elements that share something, share this particular alignment. So it helps us recognizing these models. And since the web is becoming more and more dynamic, also this common fate concept makes some sense now, because what we have is, what we'd like to know ideally is that if we click on a particular element or move our mouse over a particular element, that something happens. Of course, we cannot pass what in detail happens, but at least what we can say is something happens, because there's a JavaScript hook and there's some event handler attached to it. And we can at least say that, okay, there's the same JavaScript event handler attached to a particular class of elements. So they share something in common. They have some common fate, and they might have something together, like a navigation menu or whatever. The saliency is which about how outstanding some items are, can be calculated in a relative way just by looking at font sizes and weights and colors, and looking at the frequency of these font sizes. So we have a very straightforward way to encode this, and we come up just with a number that's also depending on color entropy, which is basically looking at in a color space, on the color space distance between two colors. That tells us how large the contrast between foreground and background is, and also, as I said, looks at these font values of an element. So we have somehow come up with a number that says, okay, this text is somehow more outstanding than some other text. So how do we do all this, and how do we write this back into the model? As I said, we have these Enrichers, which are little programs that augment the model with additional facts. We do these Enrichers. These can range from like 3 lines to a couple of 100 lines of programs, but most of them are like 20-liners. We implemented some of them in Ruby, some of them in Java. For example, using the Jena library, down there, you can see what it would look like in Jena if you want to write back a typed literal into the model. And we use Sparkle and Sparkle Update. And that's interesting because having this triple store, this now gives us a completely different way of interacting with our pages. And I'll give you an example of such a sparkled thing a bit later. And what you also can do is this automatic reasoning. Since we have in model defined in OWL and we have relations between the model, we can use a palette reasoner for checking validity in the model, which is important during development because we make a lot of mistakes, and it makes our life easier if we can identify these problems very early. And we can generalize, so we can say if something is west of something, then it's a neighbor, and we don't have to write particular rules for that. We can find out about inversion, so that if A is west of B, then B is also east of A. And if you do all that, we come up for a visual element. We come up within a lot of triples, actually. And this might be too small for you to read, but there's a lot of that in here. So how do we get it back? 3 ways, basically. We want to explore it, so somehow get a feeling of what's in there. This is being helped by statistics, which are mostly based on the frequency of properties. I'm going to show you that right now. And we can get our data back by writing queries. And these queries are written in Sparkle or in some own language that we did for that. Distribution graphs. So if you just, the font saliency that I said here before, if you just put this into a graph and you put on this particular saliency value on the x-axis and the frequency of how many items on the page have this particular value on the y-axis, you can very quickly get an overview of how these items are distributed on the page, but how many of them are. You can get this overview because, as you can see, we did a tool where you can can select ranges in this graph, and these ranges will then be highlighted directly on the web page to give you to mark exactly those visual elements that match this property. And what we can then do is we can launch additional distribution graphs like these, display additional distribution graphs like these, and make additional selections by defining additional ranges, combining these ranges with Boolean operators, and we can pretty much drill down very quickly to interesting elements on the page. If there is time, I can show you this probably after the talk. We can also query for web patterns. And the visual queries, I told you before, become Sparkle queries in our model. So if you remember the phone metaphor, basically it's about that one person on the phone should become a robot. We can, I already told you, these queries are defined in different languages. And what they should identify, basically, is web patterns that all web designers think in. So this is an example of a pagination web pattern, and then for an art, like an article teaser, it's exactly what the talk before mine has been all about. And this methodology gives us a way to describe these extractors in an alternative way. So this is a Sparkle query that will extract exactly the stuff on the page before. So this one, you have an image, you have a header, and you have some text underneath. So this is the Sparkle query. It basically selects from our triple store. It selects 3 elements, T1, T2, IMG, where the first one, T1, is an HTML text. We know that from our Mozilla component. T2 is also a text, and EMG is an image. We know that. And that all we require is that we want that a T1 is north of T2, image is west of T2, The T1 should be the larger text, so it has some font saliency that should be larger than the font saliency of text below. And that's it. That's a very primitive rule. This is just showing this to you because it's so easy to understand. But even with this very basic and primitive rule, we're able to identify many of these article teasers that are spread out on web pages. So since I'm running out of time, I'm skipping that what you can read in the paper about another way how to formulate queries. And I'm just finishing by saying what this means for accessibility. Because we are writing, we have these queries and can identify web patterns and objects in our model. We will augment also these findings of these queries back in our model and provide these elements as possible paths for visually impaired users, what we actually do. So if you have serialization of the document, which is on this black axis, and we have enricher processes that found out something about some news elements on the blue axis, we will just provide an additional way by putting it on a certain keystroke for blind users to quickly jump from one part of the element to another model line. So to wrap it up, what we did is a versatile model, basically to play around with. And this model is done in a semantic web implementation, which gives us the advantage of using Sparkle queries for actually querying visual documents in a semantic web way. We think of course, it has nothing to do with with Gestalt vision-based approaches where it can come up with a huge model of understanding from how you compose things together. But we think that these Gestalt laws give a good inspiration of what tasks and what types of information you are looking for in elements. And we did that. And we created several ways to enrich, explore, and query the model. And yeah, that's it. Thank you for your time.
There's a drumbeat of enthusiasm outside. Are there any questions for our speaker?
I thought it was really interesting. Have you tried it with blind users?
Yes.
And what was their feedback?
Well, they were very, I don't want to say enthusiastic, they were very interested because this is not a finished product that we have, but it's a proof of concept and prototype. So they were only able to play around with it in its common form. But they certainly told us that they would like to have this in a way they could use this on a daily basis.
Why didn't you use XHTML plus RDFA in order to inject inside the web page your model information? Because here your model is completely, the descriptions are completely
Our model is completely flat. Our model is now completely flat. And we just didn't want to bother with the original DOM tree because we could not see any use for this tree information in our queries after that.
Okay.
Okay.
You use Sparkle 1.1,
yeah.
Which ARQ is processing Sparkle 1.1.
ARQ, yeah.
Okay.
I'm not sure. Okay.
Are there other questions? Okay, let's thank our speaker again. For the next talk. Thank you very much.